Hello everyone, welcome to topic 8. This will be the last topic in theme 2. Topic 8, we will study game theory and conflict management. We have already studied different kinds of applications of AI and machine learning. We saw already how to, for example, searching the optimum path or for example, the searching techniques, which is tool of AI, and also we introduced the concept of intelligent agents. And we said that intelligent agent, in order to take decision, they need information, and this information is extracted from data. And we also show several machine learning techniques, and we mentioned there that the machine learning is a tool to extract information or to learn from data or extract information from data or build a model of the behavior that under study or under work. Now, once we have information, we need to have decision. So making decision usually is not easy task, because it is not related to one entity, but it is in like a set of entities that we need to have decision, which can be like conflict of interest. Let us study this in more details here. So in this lecture content, actually we will see what is game theory and examples, items of game theory, and game modeling, zero and non-zero sum games, Nash equilibrium with comparing with the optimum solution, and then we take example like prisoner dilemma and in-person games. Okay, so let us explain first what we mean by game theory. Now assume that we have like two intelligent agents, and they are fighting for the same energy. So for example, we have limited energy here, and they want to fight, or they want to negotiate maybe about how to use the available energy, because the available energy is used for both of them in the same time. So the one which consume more, it will be reduced from the portion of the other one. So game theory actually is very important. So game theory represents the mathematical foundation for analyzing the behavior of intelligent agents in responding to a conflict of interest. Yeah. So when we have more than one intelligent agent, and they are like working within the same environment or using the same resources, how they could react to each other, what kind of strategy that they should play against each other. So this is the game theory. Let us have example about a game theory application. So assume that you want to build or to make software like intelligent agent as a software that to supervise an online shop. So you have online shop that this online shop sells some gadgets, okay, and it is completely supervised by intelligent agent. And there is also another online shop. They sell the same gadgets that like the first one. Okay, and then if we assume that the number of customers that we have in one, that they will visit usually both online shops. So we have online shop A and we have online shop B, and then we have in one customer usually based on statistics that they check A and then they check B, and then they buy from the cheaper one or better offer one. And also there's N2 customer that they usually they come only to your shop usually, and they buy the gadgets from your shop without visiting B, but they buy it if the price was good for them, so or within their budget. Okay, so we have now this problem. So the intelligent agent, how they should react, what prices that they should use for the gadgets, assuming that maybe both shops, they got the gadgets with different prices, for example, from different vendors or whatever, but they are equivalent. Okay, now what kind of prices or strategy, because the price will be one of the strategies that it will be used by the intelligent agent. So what price that they should use, or maybe what kind of marketing that they will use, and so on. So these things that they need to have, because this N1, if they lose N1, of course they will lose the selling like percentage or the revenue. Okay, because they if they set the prices at high price, then they will lose this like significant part of N1, they will go to B, and also significant part of N2, they will not be able to buy it because it is outside their budget. However, if they reduce the price too much, then they might reduce their revenue per item, but they might increase as well the number of customers. So they need to have some optimization here, but, and this is the tricky part of the of the game theory, that the intelligent agent at B also they can react according to your reaction. So if you reduce the price, maybe B also will reduce the price. And then maybe you'll not get more N1 because they can get even better offer from B. So how to play such kind of game? Okay, how to set the mathematical foundation of such kind of like problems. Let me sorry. Let me give it in mathematical form. So now assume that we have two intelligent agents, X and Y. The reward function of X is this one. This is the reward function. It is 5X minus 6Y. The reward function of Y is given by this equation, minus 2X plus 2.5Y. Okay, now you can see that whatever that you X get, because you can control X. X can be that the parameter that X can control. Y is the parameter is intelligent agent Y can control. Now let us assume that X and Y is between minus 1 to 1. So X is between minus 1 and 1, and Y also between minus 1 and 1. Okay, it is clear that for X, for the intelligent agent X, in order to maximize its reward, they should put X at maximum. So if they put X at the maximum value, for example, the maximum is 1 here, then they will get UX equal to 5 minus 6Y. But the problem here that their reward depends on the selection of Y. So it is not depending on X itself. And this is the like a critical difference between game theory or and normal optimization problem. In the optimization problem, that you set your parameters in order to maximize your reward, but it will be only depending on your own parameters. But if the parameters depend on some other intelligent agent that they can control them, then the problem is not that easy to handle, or the reward is not that easy to obtain. Okay, now if you decide to put X at 1, then you will have 5 minus 6Y. And if intelligent agent Y decided to put its value, because they can also select the strategy between minus 1 up to 1, if they put Y equal to 1, then actually you will lose because you will get minus 1. Okay. However, for Y, actually they will win anyway, because if you put X equal to 1, that becomes minus 2, but they can put also Y equal to 1, it becomes plus 2.5, and then the result becomes 0.5. So they can get some positive reward, but you will get negative reward. Okay, so in case that this game is played by X and Y, if X and Y are intelligent and mature or rational, then of course uy will put it equal to what? Equal to 1. And of course ux will put it equal to 1 in order to minimize their own losses. If X and Y are friends and they decide that, okay, we shouldn't harm each other, and they collaborate and they have good communication between them, and then X asked Y, please put your Y equal to 0 and I will put my X equal to 0, then we will be fair. So I will lose nothing, but you also will lose nothing. So in that case, if they put both X and Y equal to 0, then your X will be 0 and your Y will be 0. But do you think that this is possible? At what condition this should happen? Actually, Y will sacrifice if they accepted such kind of offer, because they have the opportunity to get 0.5. There is another thing here. If X decided to reduce from 1 to 0, Y actually can exploit this opportunity and put Y equal to 1, and in this case Y will jump from 0.5 that they will what they can get up to 2.5. Okay, so Y can actually exploit this mistake of X if X decided to put X equal to 0, and in that case X will lose a lot. Instead of losing only -1, in this case, because they put X equal to 0 and Y becomes 1, they will lose -6. So you can see that they can lose a lot. So actually the solution that X equal to 1 and Y equal to 1, in this case we call it equilibrium solution. Because in that case, if any of them deviate from this one, the other party can get benefit from this deviation. No one can do better than this one. Okay, so but to play such kind of game, we need the intelligent agent to be intelligent enough to understand these concepts. Of course, this example is extremely simple example, but we can see that much more complicated examples, as maybe not in this lecture, but in game theory, we have much complicated cases that the intelligent agent needs to run a lot of routines or computer codes in order to find the equilibrium solution or the best solution that they can do. Okay. So we saw that the selection of the strategy in this simple example, that X or Y needs the agent to be intelligent, rational, and mature, that to select the best X and Y to play. Now, if we compare this type of decision making in artificial intelligence with that one of the agents that we need to find the best route from Vaasa to the airport, we can see the difference between these two types of problems. The best route finding is an optimization problem based on some searching techniques, but the two agent problem that requires different kind of math to find the equilibrium point, as we will explain. So conflict problems, actually, when we have conflict problems like this one that we describe it, they can be sequential or non-sequential. Sequential means that it is one by one. It is like, for example, in chess game. So first player play and the second one respond. So this is called sequential game. Or maybe there are two countries, and the one country they might take decision based on the action of another country. So or maybe you start in your work environment, you might take some action based on your boss decision about something. So it can be sequential. So sequential means that one agent takes the decision after another agent. So it is sequential game. It's called sequential game. It can be also non-sequential. Non-sequential means that no one depends on the other, so they can be in the same time actually. So no one knows what is the strategy taken by someone. So they make their own decision independently. So it is non-sequential game. Okay. The games can be cooperative and non-cooperative. The cooperative game means that the two players, they have some communication together, and they think that if they cooperate, then they might get better like reward or revenue for both of them. So both of them, they can get better payoffs if they cooperate than if non-cooperate. Okay, so they can cooperate. Maybe, of course, there are some other reasons. Not only, by the way, when we talk about payoffs, we don't mean necessarily that some kind of money. It can be also some moral, or it can be some like political achievement, or it can be anything. So payoffs is more general term about that everyone try to achieve as much as possible, or as high as possible. Or of course payoffs, sometimes it can be losses, and in that case we need to minimize it. Okay. So non-cooperative game means that everyone like makes their decision independently from the other. So everyone looks to it is or their own interest. What is the best strategy the player could play independent of the other? So they know the other that they will play also like in the best way. So how every player, if we don't have communication between them, how every player will play. Okay, as we saw in the previous example of ux and uy, we saw that by default that x and y, they will play both of them independently. They will play with one, because with one, y could maximize their like utility, and x, even they know that they will lose, but at least they will minimize their losses. Okay. So in optimization, or in mathematics, we call this such kind of problems min-max problems, or minimum maximum. One player try to maximize and the other player try to minimize this player. So it is min-max problem usually, especially for the zero-sum game, as we will see shortly. Okay. Yeah, so this is the same example that we have seen. Okay, so game theory means conflict analysis. Okay, game theory means conflict analysis, how to analyze the conflict, and also it can also suggest what is the proper solution, or the proper response for that situation. Okay, so in any game we need the player to be rational, intelligent, and decision maker. So these three conditions are required for in general game theory. Okay, and the items of game theory in general, the game theory consists of four things at least: players to play the game rules and available strategies, because for every game there is rules, and for every player, he or she or it should have set of strategies that they can play at each stage. And then objectives, that every player should have some objective to achieve that they want, for example, to maximize, other player might want to minimize. We might have like a zero-sum game where one of the players, they don't want to maximize their revenue or their income, but they want just to make the other player lose. So it depends on the objectives. So the strategy, the optimum strategy depends on the objectives. Okay, and finally the payoffs. The payoffs should be clearly defined. So we should have all these four items clearly defined: the players of the game rules and the strategies available for each player, and objectives for each player, and the payoffs equations, utility function, or whatever available for every player. So in that sense, we can define the game as that omega is the set of players, can be up to n players. Then we have SI is the set of strategies available for every player. For example, when we say S1, it means that the set of strategies available for player 1. S2 is the set of strategies available for player 2, and so on. UI is the utility or the payoffs function of each player. So U1 is the utility or the payoff of player 1, U2 is the utility or payoff of player 2, and so on. Then we have finally T is the time. So actually it depends on the time. So in dynamic games, it is also time dependent. So the utility function might change. So U1, for example, it might be function in T. So for example, you start the game that with certain utility that or payoff that you want to achieve, but within time you change your payoff. Okay, or the strategy itself. So the strategy depends on the many other things in the environment, for example. So the strategy, for example, for the player 1 can be also function in T. So time here is also important to be added into the general games. Okay, game modeling. Game modeling, anything that we want to solve or to handle, the first thing that we need to do is to model it. So modeling is very, very important. Okay, now we have different kind of models in games. One model is called strategic form. What is the strategic form of games? Let us take bimatrix or only 2 players. Of course, this one could be extended for any number of players, but we will take only two players. Player 1 and player 2, as you can see here. And each player, here we assume that we have like a discrete set of strategies. The strategy can be continuous, can be, for example, as we saw in the first example, when we talk about UX and UI, we said that the strategy of X is between -1 to 1, which is like a continuous number. Okay, this is, for example, can be let's say voltage, for example, if we are dealing with within some circuit, for example. Or it can be, of course, if it is greater than 0, from 0 to, for example, 2, this can be the power, transmitting power. If we have like the agents we try to optimize or to handle certain telecommunication channel. For example, we have multiple users, and all users they use because all users in the downlink, for example, from the base station to the mobile phones, they use the same battery, the same energy of the base station. How to like manage this energy between users? This can be formulated as a game in the game theory. So, however, that here we assume that we have different or discrete strategies. So, player 1 has strategy 1, strategy 2, up to strategy n. Player 2 has strategy 1, strategy 2, up to strategy m. They don't need to be equal. So every player might have different number of strategies. Okay. Now, if player 1 play with strategy 1 and player 2 plays with strategy 1, then player 1 will receive A11 and player 2 will receive B11. 1 here, the first one means, or the first index here for the strategy number of player 1, the second one is the strategy number of player 2. If player 1 plays with strategy 1 and player 2 plays with strategy 2, then player 1 will receive A12 and player 2 will receive B12. And so on, actually, up to B1, A1M, B1M, and finally we have if player 1 plays with strategy N and player 2 plays with strategy M, then player 1 will receive A and M and player 2 will receive B and M. So this kind of modeling is called strategic form. It's called strategic form. Okay, so every player will try, for example, for player 1, they will try to play the strategy which maximize it is like a chance of or maximize their payoff. Player one, they will play the strategy which maximize their payoff, and they know that player two will play the strategy also that they will maximize their payoff. So now, which one player one should play and which one player two should play? This is what we will explain and we will show in this lecture. Okay, zero-sum game. In the zero-sum game, it means that every reward or everything, every payoff received by one player, it will be subtracted from the other player. Okay, any payoff or any revenue obtained by one player will be subtracted from the other player. So in this case, we say that Aij plus Bij equal to K, and K is constant. It means that if you increase B, it will reduce A by the same amount. If you increase A, B will be decreased by the same amount. So it is always, they are zero-sum game. Of course, K can be zero. If K, generally K can be any number, but can be zero. When it is zero, for example, like in chess game. Okay, so in chess game, for example, there is, and we assume that the draw is not allowed, then there is only one player that should win. So it is zero-sum game. It is not possible that both players will win. Okay, and for K, which is not zero, example, if you assume that in certain country we have a rule that each person must be subscribed with one mobile operator. So we have two mobile operators, A and B, and each user or each customer must be subscribed in only one of them. So what happened now? So if you make the strategy to take as more customer that you take A, it will be reduced from B, because here the number is fixed, is the number of population N. So the number should be divided between A and B, but how it will be like divided? Is it equally likely or with different percentage? So every operator now, they start to provide many like offers in order to attract more users. So more customers means that reduced from the other player. Of course, this is in the case that they play non-cooperative game. Of course, usually the authorities in certain country, they will try to observe and to avoid such kind of cooperation between players, between for example, phone operators, that they can cooperate in order that to raise the prices and so on. So but usually the authorities, they should take care that there's no cooperation between operators in order to make this market under like fair competition, so they can provide better or the best prices for customers. Okay, so now we can see here that in the case of two players payoffs matrix, so this is the payoff of player one, and this is the payoff of player two. In case that we have a zero-sum game with K equal to 0, of course in this case B is just the inverse of A, because as we said that Aij plus Bij equal to 0. So in this case, Bij equal to minus Aij. So as we can see it here. So this is the case of zero-sum game. Okay. Now let us start with to explain these concepts with few examples. So assume here that we have two players, X and Y. Each player has two cards. One is red and one is red and the other one is black. So each player has two cards, red card and black card. Okay, both players should throw one card at the same time. So in both of them, they will throw one of them. If both cards were red, then player X wins $1 from player Y. And if both were black, player Y wins $1 from player X. If both cards have different colors, it is fair. So no one will lose or will win. Okay, so now of course it is a very trivial game. Okay, so because player one either they will either win or be fair if they throw red, and the player two will be either win or fair if they play with black. However, if the inverse, then it can be either like fair or losing. Okay, so in that case, of course, player one will always play with red, and the player two will always play with black. But let us put it in mathematical or in this bi-matrix form. So now if player X can play red one strategy to black. Okay, player Y can play also first strategy red, second strategy is black. If player X play red and player Y play red, of course player 1 will get 1 and player 2 will get -1. And if player 1 play red and player 2 black, of course will be 0-0 because both of them it will be fair. And also black red is 0-0. And if it is black black, then player 1 will lose -1 and player 2 will receive 1. Okay, so in that case it is clear that this game is 0 game. So if you add 1 minus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, minus 1 plus 1 is 0. So it is 0-sum game. So the summation is always 0. And this is the matrix of player 1, and this is the matrix of payoff matrix of player 2. Now, later when we show how to solve such kind of problems, we will find that the optimum solution or the equilibrium solution here will be like 0-0. Okay, because player X will play with red always, and the player Y will play with black always, and this will be the equilibrium solution. No one can do better if deviating from this selection. They cannot do better than this one. Okay. Of course, it is zero-sum game, so it is not necessary always that we show both of them. So in zero-sum game, that we just show one of the result. For example, we show here the result of X, so it is enough because we know that when X get 1, it means that Y minus 1. If it is 0, we know that Y is 0. 0, Y is 0. When it is -1, we know that Y is 1. So it's not necessary that we put both of them every time. Okay, now we take another example. It can be a little bit more like lengthy. It is not difficult, but it is longer type of games. So the idea here that we have two players, A and B, and each player and in front of each player there is two locations or two places, and each place there is two cards. Don't care about the content of the card or the card type, but you have only two cards at A and two cards at B. So this is location A and this is location B. So we have two locations in front of you and your opponent, and we have two cards in each location. The game is like that. Assume that A always start. So when A start play this game, they have the right first to select A or B. Okay, so player 1 selects A or B location, and then they have the right to draw one or two cards. So for example, if player 1 selected location A, then they can play, they can draw only one card and leave one, or he or she has the right to draw both of them. Okay, then second player, they select the location where there is still cards, and also they have the right to draw one or two cards. Okay, and then player 1 comes again to play, and it will be in this way. this is the game. So the game is based on just the first player select the location, draw 1 or 2 cards, and then the player 2 select the location where there is still cards and select 1 or 2 cards, and then player 1 play again. The loser is the one who draws the last card. So the last card is the loser. For example, if player 1 decided to select, for example, A, and player 1 take both cards, okay, then player 2 when start, of course they have only location B. So if player 2 is not smart or is not clever, so he will draw both cards. When he draw both cards, then he loser. Player 2 will be the loser in this case, because he draw he makes this like locations empty. But if player 2 in this case draw only 1 card, then he will left 1 card. Then player 2, so player 1 now, the turn of player 1, they will have only B location with 1 card, and then it will be the last card. Then in this case, player 1 is the loser. So this is simply the game. Now, how could we build the pi matrix of this game? First, we can put it in the extensive form. Okay, now we put it in the extensive form. This will be the extensive form of this game. Let us explain it now. So we can see here that, as we explained now, this is 2 locations where we have 2 cards and 2 cards. Okay, now player 1 plays first. Okay, player 1 starts. So player 1, how many strategies for player 1 that they have? Player 1 has only 2 strategies. They can take only 1 card from 1 location, so it can be 1, 2, and can also draw 2 cards from 1 location, so it is 0, 2. Of course, here the location doesn't have any meaning. In that case, there is nothing related to the location itself. Is it A or B? For that sense, it is 1, 2 or 2, 1 is actually the same. And 0, 2 or 2, 0 is the same. For this reason that we will not make these options. So it is the same. So there is no points for the location itself. Okay, so we will not go through the based on the location. So it will be the same. So now they have only 2 strategies. Player 1 in the beginning, in the starting, they have only 2 strategies. Either play 1 card, it will be 1, 2, or removing 2 cards, it will be 0, 2. Then we have player 2 now plays. Now this is the turn of player 2. Player 2, they can play either 0, 2, okay, or 1, 1. 0, 2, it means that they remove only 1 card. Or 1, 1 means that they remove 1 card from here. Or 1, 0, it means that remove 2 cards from here. So they have three strategies from here. For player 1, if they play 0, 2, then player 2, they have either to play 0, 1, they remove only 1 card, or they remove 2 cards, so it becomes 0, 0. Okay? Then player 1 comes again. So if it is here, so of course 1 wins. If it is here, we cannot say that we have a strategy here. There's no strategy because you have only 1 option. Since you have 1 option, it means that there is no strategy. So player 2 wins here. Okay, if player 1 is here now, player 1 doesn't have any strategy because they will lose anyway. Okay, here also losing. The only option that they have, if it is 0, 2, if it is 0, 2, then they have 2 strategies, either play 0, 1 or 0, 0. Okay, so the game is ending here. So here is 1 wins, here is 2 wins, 2 wins, here 1 win, and so on. Okay, so this should be very clear. Okay, now let us say what is the total strategy, the strategy form of this game. So the strategy form is like that. And now let us see the total strategies for player 1. Player 1, the strategy play 1-2. Okay, this is one strategy, play 1-2. If at 0-2, if, for example, this is the play 1-1-2. This is one play 1-2. Then if at 0-2, if the player at 0-2, then how many strategies they have? They have two strategies, either play 0-1, then this is one strategy because ended now. Play 1-2. If at 0-2, it means that if player 2 plays 0-2, if at 0-2 play 0-1, then play 1-2. If at 0-2 play 0-0. Okay, and this is the second strategy. The third strategy, play 0-2. Of course, here we don't say that if at 0-1 or if at 0-0 because there is no strategies, there is no options, there is no choices for player 1 to select. So actually player 1 has only 3 strategies to play. The total strategies that when you make the extensive form of the strategies, you bought all strategies, either you win or you lose. All the strategies that you bought. So player 1 has only 3 strategies, either play 1-2, if at 0-2 play 0-1, play 1-2, if at 0-2 play 0-0. We don't say that if at 1-1. Why? Because there's no choices. We don't say that if at 1-0 because you have no choices here to select. The strategy is where you have choices to select. Okay, for player 1, player 2 is different. Player 2, they can say that play, because player 2 now is here. Okay, at 1-2. Then if at 1-2 you can play either for example 0-2, or you can play 1-1, or you can play 1-0. So you have 3. If at 0-2 you can select 0-1, or you can select 0-0. Okay, then if at 1-2, for everyone you have like 3 of them, then you will have 6 strategies as explained here. Yes, this is the game itself. So you can see that we bought them here. So you can also study them yourself from the slides. So this is the strategies for player 1, play 1-2, then if at 0-2 play 0-1, play 1-2, if at 0-2, as I said that you put all possibilities, either you win or lose, either player win or lose. Strategies for player 2, they put all strategies that if at 1-2, if they found them at 1-2, then they can play 0-2. But if at 0-2, they can play 0-1. Okay, because here, if you can see, we have here at 0-2, you can move 3 times at 0-1 because we have 1-2 at 0-2, 1-2 at 1-1, 1-2 at 1-0. And then we have also 3 times 1-2, the same, we repeat them here because we have another chance that if player 2 at 0-2, they can play at 0-0 or 0-0 or 0-0. So it is actually, it can be easily explained or tracked from this form. So it is called extensive form. So extensive form means that if at 1-2 play 0-2, if at 1-2 play 1-1, if at 1-2 play 1-0, and if at 1-2 play 0-2, but if at 0-2 play 0-1, and so you put all possible strategies that player 1 and 2 they can play. So even in this simple game, we can see that we have six strategies for player 2, and we have 3 strategies for player 1. Now we can build easily the by matrix. So we bought them, the strategies of player 1. We have only 3 strategies. For player 2, we have 6 strategies. And here we bought for player 1 the payoff. So because it is zero-sum game, so when we say that here is 1, it means that for the player 2 is -1. Okay, so now we have if player 1 plays with the strategy 1 and the player 2 plays with the strategy 1, then player 1 will win. because it is +1. If player 1 plays with strategy 2, player 2 plays with strategy 1, then player 1 will lose and player 2 will win. Now, when we fill this matrix, of course, this matrix is based from the previous like extensive form that we know who win and who lose. And now when we have this, so if player 1, which one they should select? If they look here, actually they can select any of those, because any of them, depending on the player 2, they can win or lose. For example, if they select to play with strategy 1, then player 2 plays with strategy 1, it means that player 1 will win. Of course, player 2 will never play strategy 1. Player 2, if plays with strategy 2, it means that player 1 will also win. Okay, so they will never play it strategy 2. But if they play with strategy 3, then player 2 will win and player 1 will lose. Okay, so if player 1 plays with strategy 1, then of course player 2 will play with strategy 3. Okay, and so on. You can see here, based on this by matrix, that player 2, if they play strategy 5, then whatever player 1 plays, player 1 will always win. Okay, so what that mean? It means that player 2, if they are mature and intelligent, of course, they will never play strategy 5. And if player 2 plays with strategy 3, it means that whatever player 1 plays, then the player 2 will always win. Okay, so what that mean? It means that player 2, of course, they will always play with the strategy 3. Okay, so this game, it has dominant answer or dominant solution that player 2 will always win. So it means that in this game, this 2-card game, the player 1 will be always loser as far as player 2 is playing next. So the first player is always will lose, but at one condition, that both they are intelligent, mature as well. So if they are not intelligent enough, of course it can lose. But here you can see that if player 2 plays with strategy 3, they will always win regardless of player 1 what they take the first action. So here the first player is always loser. The second player is always winner by playing this strategy. Okay, so this is called dominant strategies. This is called dominant strategies because it is known that player 2 will always play with the strategy 3, and the player 1 doesn't have any other option to deviate from this case. Okay, so it is called dominated strategies as it is shown here. Okay, yes. So the extensive forum actually it gives you how to win, for example, 100%. Of course, games with where you know who's the winner and who's the loser, even in for fun games, is boring game. So no one like to play such kind of games actually, as far as we know how to win every time. Okay. However, that for example, if we take the game like chess game. For the chess game, where we have 64 square here, actually the number of the extensive, the number of strategies for both games, for example, if play this, then if play if, and so on. So if you can put this extensive form, actually the number of options is more than the number of atoms on Earth. Okay, so it is a huge number. It is maybe 10, I don't remember now the number, 10 of the power, maybe 47 or something like that. It is a very huge number. So it is impossible to build the extensive form of the chess game. And actually this makes it like attractive to people to play. Otherwise, if we know how to win 100%, then of course it is not, it becomes not attractive anymore. Okay. And when we talk about real problems or practical problems, things can be even more complicated if we include also the uncertainties and so on. Okay. Yes. Okay, I think now we are close to 1 hour, so we can stop here and we continue in the next part. Thank you very much.